Hello and welcome back to the Sleepy Science channel. I'm glad you're here, wherever you're listening from, whatever kind of day you've had. If you're the sort of person who finds comfort not in silence, but in soft, slow facts about the universe, then you're exactly where you're supposed to be. Tonight, there's nothing you need to do. No decisions, no plans, nothing to solve. You can let your eyes close whenever they're ready. You can let your breathing slow down on its own. You don't have to listen to every word. You don't have to remember any of it. You can simply let the sound of this voice carry you somewhere far away, out past the rooftops, out past the clouds, out into the quiet dark where the stars are still burning the way they have for billions of years. Tonight isn't about one galaxy or one mystery. Tonight is a wandering journey through some of the strangest, gentlest, and most wondrous facts about the universe itself. The kind of facts that make the world feel a little bigger and your worries feel a little smaller. We'll talk about time so vast it barely makes sense, about light that left its source before humans existed, about objects so strange they break the rules we thought were unbreakable, and about the quiet, surprising ways that you, right now, lying in bed, are connected to all of it. There's no rush tonight. We have all the time we need, and the universe certainly does. So get comfortable. Let your shoulders relax. Let your jaw unclench. Let the blanket settle around you. And if you find that these calm explorations help you drift off, it would mean a lot if you considered subscribing to the channel so future episodes can find their way to you on nights like this one. Now, let's begin. Right now, as you lie there, light from the sun is touching your skin that left the sun about 8 minutes ago. That's how long it takes sunlight to cross the 93 million miles between the sun and the earth. Every beam of warmth you've ever felt on your face was already on its way to you minutes before it arrived. The sun doesn't know you're here. It simply keeps shining, the way it has for about 4.5 billion years, and that light just happens to fall across our small blue planet on its way outward into space. If the sun suddenly vanished this instant, we wouldn't know for 8 minutes. The sky would look completely normal, completely lit, completely fine. For 8 more minutes, until the moment the last bit of light that had already been sent arrived, and then everything would change. It's a strange thought that the present moment for the sun and the present moment for us are not quite the same present moment. We are always looking very slightly into the past. The stars you see at night are even further behind in time. Some of that starlight left its source hundreds, thousands, or even millions of years ago. When you look up at a clear night sky, you are not seeing the universe as it is. You are seeing a collection of old messages, some recent, some ancient, all arriving at your eyes at the same moment, despite having traveled for wildly different lengths of time. A star that looks steady and calm might have already changed completely, might have swelled, faded, or even ended its life, and the light telling us otherwise simply hasn't arrived yet. In a way, the night sky is less like a window and more like a very old photograph album. Pages from many different years all open at once. Distances in space are so large that scientists had to invent a new way to talk about them. A light year isn't a measure of time, even though it has the word year in it. It's a measure of distance, the distance light travels in 1 year, moving at about 186,000 miles every single second. In 1 year, light covers nearly 6 trillion miles. The nearest star to our sun, a star called Proxima Centauri, is about 4.2 light-years away. That means the light reaching us from that star tonight left it over 4 years ago. If you sent a message there at the speed of light, it would take more than 4 years to arrive, and another 4 years for a reply to come back. A simple conversation would take almost a decade. Space isn't just big. It's big in a way that makes the idea of a quick chat between neighboring stars almost meaningless. And yet, even with distances like that, the universe still has room to surprise us. Out in space, there are objects so dense that a teaspoon of their material would weigh more than a mountain here on Earth. These are neutron stars, the collapsed cores of stars that once were many times larger than our Sun. When a massive star runs out of fuel, it can collapse so violently that its outer layers explode away in a supernova, while its core gets crushed down into a sphere only about 12 miles across, yet still containing more mass than our entire Sun. The gravity on the surface of a neutron star is so strong that if you dropped an object from a height of just 1 meter, it would hit the surface at thousands of miles per hour. Some neutron stars spin incredibly fast, some completing a full rotation many times every second, sweeping beams of radiation around like a cosmic lighthouse. We call these spinning ones pulsars, and their rhythm is so steady that early astronomers briefly wondered if they might be signals from somewhere else. Black holes are even stranger. A black hole forms when matter is compressed into a space so small and so dense that gravity becomes overwhelming, strong enough that nothing, not even light, can escape once it gets too close. The boundary around a black hole, the point of no return, is called the event horizon. Beyond that boundary, we genuinely don't know what happens because nothing that crosses it can ever send information back out to us. Some black holes form from dying stars. Others, found at the centers of galaxies, are millions or even billions of times more massive than our Sun. Our own galaxy, the Milky Way, has one of these supermassive black holes at its center, though it's calm right now, quietly sitting there, while stars orbit around it at incredible speeds, the way moths might circle a porch light without ever quite touching it. Time itself behaves differently depending on where you are and how fast you're moving. This isn't science fiction, it's something we've actually measured. Clocks on airplanes, on satellites, even on mountaintops, run at very slightly different speeds than clocks at sea level because gravity bends time, and so does speed. Astronauts on the International Space Station, traveling at about 17,500 miles per hour, age very slightly slower than people on Earth, just a tiny fraction of a second over months in orbit, but it's real and it's measurable. If you could somehow get close to a black hole without falling in and then return to Earth, you might find that years had passed for everyone else, while only days passed for you. Time isn't a steady drum beat playing the same for everyone everywhere. It's more like a river that flows at different speeds, depending on where you stand in it. There's a number that astronomers use almost casually that, if you actually stop to think about it, is almost impossible to hold in your mind. The observable universe is estimated to contain somewhere around 2 trillion galaxies. Not 2 trillion stars, 2 trillion galaxies, and each of those galaxies can contain anywhere from a few 100 million to several trillion stars of their own. If you tried to count every star in the observable universe, one per second, you would still be counting long after the Sun itself had burned out. And that's only the part of the universe we can observe, the part close enough and old enough that its light has had time to reach us since the universe began. There may be far more beyond that boundary, regions whose light simply hasn't had time to arrive yet and might never arrive, because the universe itself is expanding, stretching the space between everything. including the space the light has to travel through. That expansion is one of the strangest things about our universe. Galaxies aren't just moving away from each other through space. The space between them is actually growing. Imagine drawing dots on the surface of a balloon and then slowly inflating it. The dots themselves don't move across the surface, but the distance between every pair of dots increases as the balloon expands. That's roughly what's happening to galaxies, except in 3 dimensions and on a scale that's hard to visualize. The further away a galaxy is, the faster it appears to be receding from us, not because it's moving especially quickly through space, but because there's simply more expanding space between us and it. Some very distant galaxies are receding so fast that their light, even traveling at the fastest speed possible, will never reach us. They're not moving away faster than light through space, but the space itself is stretching faster than light can cross it. It's a gentle, quiet kind of vastness, expanding while we sleep, expanding while we wake, expanding at a pace too slow to notice in a single lifetime, but relentless across billions of years. If we rewind that expansion all the way back, we arrive at a single moment, often called the Big Bang, about 13.8 billion years ago. It wasn't an explosion in the way we usually picture explosions, with debris flying outward into empty space. It was more like the beginning of space and time themselves. Everything that exists now, all the matter, all the energy, all the room for things to happen in, emerging from an incredibly hot, incredibly dense state and beginning to expand and cool. In the earliest fractions of a second, the universe was so hot that not even atoms could exist, just a soup of basic particles. As it expanded and cooled, those particles combined into the first simple atoms, mostly hydrogen and helium. It would take hundreds of millions of years before gravity pulled enough of that gas together to ignite the very first stars, and many billions of years more before galaxies, planets, and eventually small quiet bedrooms with people drifting off to sleep in them would exist at all. Every atom in your body, the carbon, the oxygen, the calcium in your bones, the iron in your blood, was forged inside a star. Hydrogen and helium were present from the very beginning, but almost everything heavier than that was created later, inside the cores of stars through nuclear fusion, or in the final violent moments of a star's life when it explodes as a supernova. When a star dies in this way, it scatters those newly made elements out into space, where they mix with gas clouds, and eventually some of that material gets pulled together again to form new stars, new planets, and on at least one planet that we know of, new life. So when people say we're made of stardust, it isn't just a poetic phrase. It's closer to a factual description. The calcium in your teeth and the iron carried in your red blood cells were cooked inside stars that lived and died long before our sun even existed. In a very real sense, you are old, much older than your birthday would suggest. The atoms that make you up have been around, in one form or another, for billions of years, and they'll continue on long after you're gone, recycled again into something else, the way they've always been. The moon is slowly drifting away from the Earth. Every year, it moves about 1.5 inches farther away, a result of the gentle tug of tides between the Earth and the moon, gradually transferring energy and nudging the moon into a slightly wider orbit. It's far too slow to notice in a human lifetime, but over hundreds of millions of years it adds up. Long ago, the moon was much closer, appearing larger in the sky, and days on Earth were shorter, because the Earth itself was spinning faster. Dinosaurs may have lived under days that were only about 23 hours long. Eventually, far in the future, the moon will be far enough away that it can no longer create the steady kind of solar eclipses we have today, where it just barely covers the sun. Right now, by what feels almost like a coincidence, the moon and the sun appear to be almost exactly the same size in our sky, even though the sun is about 400 times larger and also about 400 times farther away. It's the kind of cosmic balance that exists for a relatively brief window of time, astronomically speaking, and we happen to be here to see it. Saturn's rings are made mostly of ice, with particles ranging from tiny grains, smaller than a grain of sand, up to chunks the size of mountains. Despite stretching across hundreds of thousands of miles, the rings themselves are remarkably thin, in some places less than 100 feet thick. If you scaled Saturn down to the size of a basketball, its rings would be thinner than a sheet of paper. They're thought to be relatively young in cosmic terms, possibly formed from a shattered moon or comet that wandered too close and was torn apart by Saturn's gravity, and they may not last forever either. Saturn's gravity is slowly pulling material from the rings down into the planet itself, a gentle icy rain falling for millions of years, meaning that one day, far in the future, the rings as we know them might fade away entirely, leaving a quieter, ringless planet behind. There's a strange kind of silence that fills most of the universe, a silence that isn't just an absence of sound, but an absence of the medium that carries sound at all. Space is mostly a vacuum, and sound waves need something to travel through: air, water, some kind of matter that can vibrate and pass that vibration along. In the vacuum of space, there's nothing for sound to push against, so even the most violent events in the universe, two stars colliding, a star exploding into a supernova, happen in complete silence, at least to anyone who could somehow survive nearby without any equipment. If you were floating in empty space near an exploding star, you might see an unimaginably bright flash of light, but you would hear absolutely nothing. All of that energy, all of that violence, simply expanding outward into a silence that has no edges. It's a strange comfort, in a way, to think that even the most chaotic events in the cosmos are, from a certain point of view, perfectly quiet, and yet space isn't truly empty either. Even in what looks like the emptiest regions, there are still a few atoms drifting per cubic meter, faint traces of gas, scattered dust, and a steady bath of radiation left over from the early universe itself. This radiation is called the cosmic microwave background, and it's essentially the afterglow of the Big Bang, stretched out and cooled over billions of years until it's now just a very faint microwave signal coming from every direction in the sky. If you could somehow tune an old analog television to a channel with no signal, a small portion of that static, that snow on the screen, would actually be this ancient light. Photons that have been traveling since the universe was only a few 100,000 years old. It's one of the oldest things you can directly observe, a kind of background hum that has been quietly filling the universe since long before galaxies, stars, or planets existed, including the one you're lying on right now. Some of the most beautiful objects in the night sky are actually graveyards. Nebulae, those colorful clouds of gas and dust that appear in so many space photographs, are often the remains of stars that have already died, or the birthplaces of stars that haven't yet been born, sometimes both at once. When a star similar in size to our Sun reaches the end of its life, it doesn't explode dramatically. Instead, it gently puffs off its outer layers into space, creating a glowing shell of gas called a planetary nebula, while its core shrinks down into a small, dense, hot remnant called a white dwarf. These planetary nebulae can look like cosmic flowers, rings, butterflies, or eyes, glowing in delicate colors for a relatively short time. Cosmically speaking, before they fade and disperse, their material drifting outward to eventually become part of some future star or planet. Meanwhile, in other nebulae, dense regions of gas and dust are collapsing under gravity, slowly heating up and beginning the long process of becoming new stars. So a single nebula might contain both the ashes of an old star and the cradle of a new one, side by side, an ending and a beginning happening in the same patch of sky. Our sun, like nearly every star, will eventually run out of the hydrogen fuel in its core. This won't happen for a very long time, roughly 5 billion years from now, so there's no need to set any alarms. But when it does happen, the sun will begin to change dramatically. It will expand into what's called a red giant, growing so large that it may swallow Mercury and Venus and possibly reach all the way out to where Earth currently orbits. The sun's outer layers will become much cooler, giving it a reddish color, even as its core continues to undergo changes. Eventually, after this red giant phase, the sun will shed its outer layers, much like the planetary nebulae we just talked about, and what remains will be a white dwarf, a hot, dense remnant about the size of Earth, slowly cooling over trillions of years. It will still technically be there, just very faint, very quiet, fading gently into the dark, long after almost everything else about our solar system has changed beyond recognition. Jupiter, the largest planet in our solar system, is so massive that it actually doesn't orbit the exact center of the Sun. Instead, the Sun and Jupiter both orbit a shared point, a center of mass, that lies just outside the visible surface of the Sun itself. Every other planet in the solar system is light enough that their shared center of mass with the Sun lies safely inside the Sun, but Jupiter is just barely heavy enough to tug the Sun itself into a small wobble. If you were watching our solar system from a great distance with the right instruments, you might actually be able to detect this wobble, the same way astronomers detect planets orbiting other stars, by watching for the tiny gravitational tug a planet exerts on its star, causing the star to wobble back and forth ever so slightly as the planet orbits. Speaking of planets around other stars, we now know of thousands of them, called exoplanets, and the variety is far stranger than anything in our own solar system. There are planets that orbit so close to their stars that a year there lasts only a few Earth hours. There are planets made almost entirely of dense, glittering material that might rain down as something resembling diamonds under the right conditions deep in their atmospheres. There are planets that orbit two stars at once, giving them skies with two suns, much like certain scenes from old science fiction movies, except this is simply how things are in some corners of the galaxy. There are even planets that orbit pulsars, those rapidly spinning collapsed stars we talked about earlier, planets that somehow survived the supernova that created their strange parent star. Every year, the list of known exoplanets grows, and with it, our sense of just how many different ways a planet and a planetary system can turn out. There's something quietly comforting about the fact that water, the same substance that makes up the rain, the oceans, and most of your own body, is one of the most common molecules in the entire universe. Hydrogen is the most abundant element in the cosmos, and oxygen is one of the more common ones as well, so when conditions allow, the two combine easily, and water turns up almost everywhere. Astronomers have detected water vapor in the atmospheres of distant exoplanets, in the icy moons orbiting Jupiter and Saturn, in comets, and even in vast clouds of gas drifting between stars. Clouds so enormous that they contain enough water to fill Earth's oceans many times over, just spread incredibly thin across trillions of miles of space. Some of the moons in our own solar system, like Europa around Jupiter and Enceladus around Saturn, are thought to have entire oceans of liquid water hidden beneath thick shells of ice, kept warm not by sunlight, which is faint that far out, but by the gentle, constant flexing caused by the gravity of their massive parent planets. Somewhere in those dark, hidden oceans, sealed away from sunlight for who knows how long, conditions might exist that we don't fully understand yet, quiet places that have never seen the sky. Auroras, those shimmering curtains of green, purple, and red light that appear in the night sky near the poles, are caused by something happening very far away. The sun constantly releases a stream of charged particles called the solar wind, flowing outward in all directions. When this stream reaches Earth, most of it is deflected by our planet's magnetic field, which acts like an invisible shield. But near the poles, where the magnetic field lines curve down toward the surface, some of these particles funnel into the upper atmosphere, where they collide with gas molecules, oxygen and nitrogen, and cause them to glow, the same basic principle as a neon sign, just on a planetary scale. Auroras aren't unique to Earth either. Jupiter and Saturn, with their much stronger magnetic fields, have auroras far more powerful than ours, some glowing in ultraviolet light, far brighter than anything we could see with our own eyes, dancing quietly around their poles, mostly unseen except by spacecraft passing by. Speaking of magnetic fields, Earth's own magnetic field isn't fixed in place. It actually drifts and changes over time, and the magnetic North Pole that compasses point toward has been slowly wandering for as long as we've been tracking it, moving faster in recent decades than it used to. Even stranger, Earth's magnetic field has flipped entirely many times throughout its history, with magnetic north and south swapping places. These flips happen over thousands of years, not overnight, and they don't appear to have caused any mass extinctions when they've happened in the past, though the process probably does weaken the magnetic field temporarily, allowing a bit more cosmic radiation to reach the surface during the transition. The rocks themselves record this history because certain minerals align with the magnetic field as they form and then lock that orientation in place, creating a kind of permanent record, layer after layer, of what direction north used to be. Embedded quietly in the ground beneath our feet, Antarctica wasn't always covered in ice. Hundreds of millions of years ago, when the continents were arranged very differently than they are today, the land that would eventually become Antarctica sat in a much warmer part of the globe, covered in forests, with rivers and even dinosaurs roaming through what is now one of the coldest, most barren places on Earth. Over an enormous span of time, the slow drifting of tectonic plates carried that landmass toward the South Pole, and the climate gradually shifted until ice took over completely, locking away those ancient forests under layers of snow and ice that, in some places, are miles thick. Scientists drilling into that ice have pulled up cores containing tiny bubbles of ancient air, samples of the atmosphere from hundreds of thousands of years ago, allowing us to look back at the climate of the deep past, almost like a time capsule that's been quietly sealed and waiting. Speaking of waiting, there are tardigrades, tiny creatures, sometimes called water bears, that are barely visible to the naked eye but are famous for their resilience. They can survive being frozen to extremely low temperatures, dried out almost completely for years at a time, exposed to the vacuum of space, and even bursts of radiation that would be lethal to almost anything else. When conditions get too harsh, a tardigrade can enter a state where it essentially shuts down nearly all of its biological processes, curling into a tiny dried husk that can remain dormant for years, only to rehydrate and continue on with life as if nothing happened once conditions improve. Some have even been sent into orbit, exposed directly to space, and survived. It's a strange thought that somewhere on this planet, in a drop of water on a piece of moss, there might be a creature that has technically been to space and back, and is, at this very moment, simply going about its tiny business, completely unaware of how extraordinary that is. Bioluminescence, the ability of living things to produce their own light, is far more common than most people realize, especially in the ocean. In the deep sea, where sunlight never reaches, a huge number of creatures, jellyfish, certain fish, squid, and countless tiny organisms produce their own soft glow, sometimes to attract prey, sometimes to communicate, sometimes simply as a side effect of certain chemical reactions inside their bodies. If you've ever seen ocean waves glow blue at night, that's often caused by tiny plankton called dinoflagellates, which light up when disturbed by movement in the water. Entire stretches of coastline can glow faintly with each wave, a soft blue light rolling in and out with the tide, completely independent of the moon or stars above, a kind of living light show happening quietly in the dark water, mostly unnoticed, night after night, for longer than humans have existed to watch it. If you could somehow fall toward a black hole, feet first, something strange would happen to your body long before you reached the event horizon. The difference in gravity between your feet, which would be closer to the black hole, and your head, which would be slightly farther away, would become so extreme that you would be stretched, gently at first, then more and more violently, into a long, thin shape, a process astronomers have, with a touch of dark humor, named spaghettification. For a smaller black hole, this stretching would happen quite far from the event horizon, well before you got anywhere near the point of no return. But for a truly massive black hole, one of the supermassive ones found at the centers of galaxies, the math works out differently. The event horizon itself might be so large and so far from the densest point at the center that you could theoretically cross it without immediately being torn apart, drifting across that boundary calmly, not even necessarily noticing the exact moment it happened, before the stretching forces eventually caught up with you deeper inside. Crossing an event horizon wouldn't come with a warning sign or a sudden jolt. From your own perspective, you might cross it as gently as walking through a doorway, even though, from the outside, you would never be seen to do so at all, your light simply taking longer and longer to climb out, stretching toward red and fading, until you appeared to freeze in place forever, an image of you lingering at the edge, long after you yourself had moved on. Time dilation near a black hole creates strange possibilities that sound more like riddles than physics. If two friends were near a black hole, and one of them got closer to it than the other, even briefly, that friend would experience less time passing than the one who stayed farther away. This isn't an illusion or a trick of perception. It's a real difference in how much time elapses for each of them. There's a thought experiment sometimes described involving a person who spends what feels to them like a short visit near a black hole, only to return and find that years, or even much longer, have passed for everyone else. It's the same basic idea as the famous twin paradox in relativity, where one twin travels at high speed through space and returns younger than the twin who stayed behind. Except here, the difference comes from gravity rather than speed. Both effects are real. Both have been measured in much smaller, much gentler forms, here on Earth and in orbit, and both point to the same underlying truth. That time isn't a fixed backdrop the universe runs on top of, but something woven into the fabric of the universe itself, something that can stretch and compress depending on where you are and how you're moving. Far out beyond the orbit of Pluto, there's a vast, mostly empty region of space called the Oort cloud, a sphere of icy objects surrounding our entire solar system at a distance so great that light from the Sun, which takes only about 8 minutes to reach Earth, might take well over a year to reach the outer edges of this cloud. The objects out there are mostly small, icy bodies, leftover material from the formation of the solar system billions of years ago, drifting slowly in orbits so wide and so long that a single trip around the Sun for some of them might take millions of years. Occasionally, the gravity of a passing star, or some other gentle nudge, sends one of these icy bodies tumbling inward toward the Sun, and after a journey lasting longer than human civilization has existed, it might finally become visible from Earth as a comet. A brief visitor with a long, glowing tail, here for a few weeks before heading back out into the dark for another unimaginably long orbit, or sometimes never to return at all, flung instead out of the solar system entirely. The concept of a day isn't as universal as it might seem. On Earth, a day is about 24 hours, the time it takes our planet to complete one full rotation. But on Venus, a single day, meaning one full rotation, takes about 243 Earth days, longer than it takes Venus to orbit the Sun, which only takes about 225 Earth days. That means, in a strange twist, a day on Venus is longer than a year on Venus. Venus also rotates in the opposite direction compared to most other planets, including Earth. So, if you could somehow stand on its surface and see through its thick clouds, the Sun would appear to rise in the west and set in the east, the reverse of what we're used to. Meanwhile, on Jupiter, a day lasts under 10 hours, the fastest rotation of any planet in our solar system, despite Jupiter being by far the largest. All that mass spinning around so quickly that its equator bulges outward noticeably, giving the planet a slightly squashed shape rather than a perfect sphere. Mercury, the planet closest to the Sun, has one of the most extreme temperature ranges of anywhere in the solar system, despite being so close to our star. Because it has almost no atmosphere to trap or distribute heat, the side facing the Sun can reach temperatures hot enough to melt certain metals, while the side facing away, plunged into darkness, can drop to temperatures colder than almost anywhere on Earth. The same planet, at the same time, can be experiencing a blistering heat on one side and a deep freeze on the other, with nothing in between to soften the transition. It's a reminder that an atmosphere, something we rarely think about, something invisible and easy to take for granted, is doing an enormous amount of quiet work, evening out temperatures, holding in warmth at night, and generally making the difference between a planet that's livable and one that's a study in extremes. There's a region of the Pacific Ocean, sometimes called the oceanic pole of inaccessibility, or more informally Point Nemo, named after the captain in Jules Verne's novels. That is the single point in the ocean farthest from any land. The nearest land masses are so far away that, in certain conditions, the closest humans to anyone stationed at Point Nemo might actually be astronauts aboard the International Space Station, when it happens to be passing overhead, simply because the station's orbit can bring it closer to that spot than any inhabited shore. It's a strange, quiet kind of isolation, a place where the nearest people aren't across an ocean, but up above the atmosphere entirely, circling the planet at thousands of miles per hour, looking down at an empty stretch of blue that has no name most people have ever heard, and no one nearby at all, except, every so often, briefly, someone floating in orbit. Octopuses experience the world in a way that's almost difficult for us to imagine. Each of their 8 arms contains a large cluster of neurons, so many that a significant portion of an octopus's overall nervous system is distributed throughout its arms rather than concentrated in its brain. In a sense, each arm has a degree of its own ability to process information and respond to its surroundings, even if it were somehow separated from the rest of the body. An octopus can taste things simply by touching them, with receptors along its arms that detect chemicals in the water, meaning it experiences a kind of combined sense of touch and taste everywhere its skin makes contact. They can also change not just the color but the texture of their skin, raising and lowering tiny bumps to mimic the rough surface of coral or rock, blending in so completely that a diver might pass within inches of one without ever realizing it was there, watching quietly, perfectly still, until the moment has passed. Many animals navigate using senses that humans simply don't have. Some birds appear to be able to sense Earth's magnetic field, essentially carrying an internal compass that helps guide them during long migrations spanning thousands of miles, often returning to the very same nesting sites year after year with remarkable precision. Sea turtles, too, seem to use magnetic information, somehow imprinted with a sense of the magnetic signature of the beach where they hatched, allowing them, years later, after swimming across entire oceans, to find their way back to roughly that same stretch of coastline to lay their own eggs. Some sharks and rays can detect extremely faint electrical fields, sensitive enough to pick up the tiny electrical signals generated by the muscles of other animals hiding nearby, essentially allowing them to feel the heartbeat of prey buried in the sand before ever seeing it. These senses operate quietly, constantly, layered invisibly over the world we already know, an entire dimension of perception running alongside our own, unnoticed, the way a radio station plays on a frequency you've simply never tuned into. Trees communicate with each other in ways that have only recently become well understood. Through networks of fungi in the soil, sometimes called the Wood Wide Web, trees can send chemical signals to each other, warnings about insect attacks, for instance, allowing nearby trees to begin producing defensive chemicals before the insects even reach them. Older, larger trees in a forest sometimes act almost like hubs in this network, connected to many younger trees around them. And there's evidence that these larger trees can even share resources, sending sugars through fungal connections to smaller trees that might be struggling, particularly their own offspring growing nearby. A forest, seen this way, starts to look less like a collection of individual competing organisms and more like a single, slow, interconnected system, communicating and sharing in ways that happen far too slowly and far too quietly for us to notice in passing, but that have been going on, season after season, for as long as forests have existed. The longest living organisms on Earth aren't animals at all, but certain trees and even some simple organisms that barely seem alive in the way we usually think about it. There are bristlecone pine trees in parts of the world that are estimated to be over 4,000 years old, meaning they were already centuries old by the time many of history's most famous events were taking place. Even more strangely, there are colonies of a single organism, a type of aspen tree that spreads not primarily through seeds, but by sending up new trunks from a shared root system, so that what looks like an entire forest of separate trees might actually be one single living organism, connected underground, potentially many thousands of years old, quietly growing and regrowing trunk after trunk over a span of time that makes individual human lives look like the blink of an eye. Sleep itself is one of the strangest things biology has never fully explained. Nearly every animal that's been studied sleeps in some form, even animals that seem like they couldn't possibly afford to, animals that are vulnerable to predators, animals that need to keep moving to survive. Some birds and marine mammals have figured out a partial solution, sleeping with only half of their brain at a time, the other half remaining alert, even keeping one eye open, watching for danger while the other half rests. Dolphins do this too, allowing them to keep swimming, keep breathing, and stay aware of their surroundings while still getting some of the rest their brain seems to require. We still don't fully understand why sleep evolved in the first place, what exactly it accomplishes at a cellular level that couldn't be accomplished while awake. But every sign points to it being essential, deeply, fundamentally necessary, something built into the architecture of nearly every nervous system that has ever existed, including the one that's slowly, gently drifting toward it right now. Your body is, in a very real sense, not entirely your own. Trillions of microorganisms, bacteria, and other tiny organisms live on and inside you, particularly in your gut, and together they form something often called the microbiome. These organisms help digest food, produce certain vitamins, train your immune system, and may even influence your mood and your sleep through a complex web of chemical signals traveling back and forth between your gut and your brain. In terms of sheer numbers, the bacterial cells living in and on your body are roughly comparable to the number of human cells that make you up, an entire hidden ecosystem, a kind of internal world, going about its business in darkness and warmth, completely unseen, every single day of your life, including tonight, while you sleep. There's a quiet kind of magic in the way snowflakes form. Each one begins as a tiny speck of dust or pollen high in a cloud, around which water vapor begins to freeze, layer by layer, in a pattern shaped by the exact temperature and humidity it experiences as it falls. Because every snowflake follows a slightly different path through the air, encountering slightly different conditions along the way, no two end up perfectly identical, at least not down to the smallest details. The basic six-sided symmetry comes from the way water molecules naturally arrange themselves when they freeze, but the endless variety of branches, points, and patterns comes from the journey each flake takes on its way down, a record, in ice, of the tiny fluctuations in the air it passed through, frozen in place, and then, often, gone again within moments of landing. Rainbows, too, are more personal than most people realize. A rainbow isn't a fixed object sitting somewhere in the sky, the way it might appear to be. It's actually formed by light bouncing and bending inside countless individual raindrops, and the specific rainbow you see depends entirely on the exact position of your eyes relative to the sun and the rain. The person standing next to you is technically seeing a slightly different rainbow, formed by a slightly different set of raindrops, even though it looks like you're both looking at the same thing. If you walked toward a rainbow, it would seem to retreat, because the conditions needed to produce it from your new position would require a different set of raindrops than the ones forming it before. In a sense, everyone who has ever seen a rainbow has seen their own, a private arrangement of light just for them, never quite shared with anyone else, no matter how close they're standing. Lightning is hotter, for a brief instant, than the surface of the sun. a single lightning bolt can heat the air around it to roughly 50,000 degrees Fahrenheit, several times hotter than the sun's surface, though only for a few millionths of a second. That sudden heating causes the air to expand explosively and then contract again just as quickly, creating the shock wave we hear as thunder. Because light travels so much faster than sound, we see the flash almost instantly, but the thunder arrives later, the gap between them stretching out the farther away the storm is. On average, sound travels about 1 mile in 5 seconds, so counting the seconds between a flash of lightning and the rumble of thunder gives a rough sense of how many miles away the storm actually is, a small bit of math the sky performs for anyone willing to count along. The deepest part of the ocean, a place called the Mariana Trench, plunges down nearly 7 miles below the surface, deeper than Mount Everest is tall. Down there, sunlight has never reached, not even the faintest trace of it, and the pressure is so immense that it would crush most submarines instantly. And yet, life exists even there, strange pale creatures adapted to total darkness and crushing pressure, some of them feeding on nutrients that drift down from far above. A slow, constant snowfall of organic material sinking from the sunlit world down into the silence below, a process that can take weeks for a single particle to complete its journey from the surface to the bottom, falling gently the entire way through complete and permanent night. Glaciers move, slowly, but they move, flowing almost like very thick, very slow rivers under the pull of gravity and their own weight. Some glaciers shift only a few inches a year, while others can move several feet in a single day, especially where they meet the ocean and begin to break apart into icebergs. The ice within a glacier can take centuries, sometimes thousands of years, to travel from where it first formed, high in the mountains or at the heart of an ice sheet, down to where it eventually melts or breaks away. Trapped within that ice are tiny pockets of ancient air, as we mentioned earlier, along with dust, pollen, and even ash from volcanic eruptions long past, layer upon layer, each one a thin record of a single year, stacked up over millennia, slowly sliding downhill the entire time, carrying its long memory with it toward an ending it won't reach for a very long time yet. Caves can contain some of the strangest landscapes on Earth, formed entirely without sunlight, shaped instead by water, slowly dissolving rock over thousands or millions of years. Stalactites hang down from cave ceilings, formed drop by drop as mineral-rich water drips and slowly deposits tiny amounts of calcium carbonate, while stalagmites build upward from the floor below in the same painstaking way. Some of these formations grow only a fraction of an inch every century, meaning a single stalactite a few feet long might represent tens of thousands of years of patient, dripping growth, each drop adding an amount so small it's essentially invisible, yet adding up, over an unimaginable span of time into something solid, something that will still be there long after everyone who ever saw it has gone deep within the earth, beneath the crust we walk on. Temperatures rise dramatically the further down you go. At the very center, the inner core is thought to be roughly as hot as the surface of the sun, yet it remains solid. Not because it's cool enough to be solid, but because the pressure down there is so extreme that it keeps the iron and nickel compressed into a solid form, despite the heat. Surrounding that solid core is a layer of liquid metal, swirling slowly, and it's this movement, this slow churning of liquid metal deep below our feet, that generates Earth's magnetic field, the same field that creates auroras, guides migrating birds, and gently deflects harmful particles from the sun. All of that, the compass in your pocket, the northern lights, the protection from solar radiation traces back to a slow, hot, churning ocean of metal, thousands of miles beneath the ground that none of us will ever see directly, and yet all of us depend on every day without ever thinking about it. There's a moon orbiting Saturn called Titan that, in some ways, feels like a strange echo of Earth. It has a thick atmosphere, thicker than Earth's, and it has weather, clouds, rain, rivers, and even lakes and seas. But the rain isn't water, it's liquid methane and ethane. Substances that gases here on Earth but exist as liquids on Titan because of its extreme cold, with surface temperatures hundreds of degrees below anything found naturally on Earth. Probes that have landed there have shown a landscape with what looks remarkably like a riverbed, smooth stones shaped by the gentle flow of liquid over a very long time, just not the liquid we're used to. It's a place that, if you squint, in pictures, looks almost familiar, almost like a foggy, orange-tinted version of certain remote places on Earth, until you remember that everything liquid there would freeze your blood solid in moments, and everything you'd recognize as solid ground might be made of materials that, here, we only ever encounter as gas. Mars has the largest volcano in the entire solar system, a mountain called Olympus Mons that's roughly 3 times the height of Mount Everest, and so wide that, if you were standing on its slopes, the curve of the mountain itself would likely be too gradual for you to tell you were on a volcano at all. The slope might simply look like flat ground stretching toward a horizon that curves away more sharply than you'd expect. Because Mars is smaller than Earth, Olympus Mons is so enormous partly because Mars doesn't have the kind of shifting tectonic plates that Earth does. On Earth, volcanic hotspots tend to create chains of smaller volcanoes as the crust slowly slides over them, like a conveyor belt passing over a flame. On Mars, with no plates sliding around, a hotspot can just keep building the same volcano, taller and wider for hundreds of millions of years, with nothing to interrupt it, until it becomes something almost more like a small mountain range unto itself, quiet now, but a reminder of just how much time, uninterrupted, can accomplish. Venus, despite being our nearest planetary neighbor in some ways, is one of the most hostile places in the solar system. Its atmosphere is so thick and so heavy that the pressure at its surface is similar to what you'd experience nearly a mile underwater on Earth. Combined with a runaway greenhouse effect, this gives Venus the hottest surface of any planet in our solar system, hot enough to melt lead, even though Mercury is actually closer to the Sun. The clouds on Venus aren't made of water either. They're made largely of sulfuric acid, and the entire planet is wrapped in a thick, yellowish haze that has never lifted long enough for any spacecraft on its surface to survive for more than a few hours before the heat and pressure destroyed it. And yet, high up in Venus's atmosphere, at a certain altitude, the temperature and pressure become surprisingly close to conditions on Earth, mild enough that some scientists have wondered, whether some kind of life might exist floating in that thin band of clouds, far above the crushing heat below, a strange, narrow pocket of almost gentle conditions sandwiched between the cold of space and the inferno of the surface. Far beyond the orbit of Neptune lies a region of small icy worlds, including Pluto, which was once considered the 9th planet before being reclassified. Pluto has a moon, Charon, that's so large relative to Pluto itself, about half its diameter, that the two don't quite orbit each other the way most planets and moons do. Instead, they both orbit a point in space that lies between them, outside of Pluto entirely, which means that, in a sense, Pluto and Charon are more like a pair locked in a slow embrace spinning around a shared empty point in space, each one always showing the same face to the other, the way two dancers might face each other and turn in place together, never looking away, for as long as anyone has been watching. Comets are sometimes described as dirty snowballs, a mix of ice, dust, and rocky material that spends most of its long orbit far out in the cold, dark outer reaches of the solar system. As a comet approaches the Sun, the increasing heat causes some of its ice to turn directly into gas, a process called sublimation, releasing dust and gas that form a glowing cloud around the comet's core, and often a long tail that can stretch for millions of miles, pushed outward not by the comet's motion but by the pressure of sunlight itself and the solar wind. This means a comet's tail doesn't trail behind it, like the tail of a moving car. It always points away from the Sun, regardless of which direction the comet is actually traveling, sometimes even appearing to point ahead of the comet as it moves away from the Sun on the outbound leg of its orbit. A tail that for a little while leads the way rather than follows. The asteroid belt, a region between the orbits of Mars and Jupiter, often depicted in movies as a dense, dangerous field of rocks you'd have to dodge and weave through, is actually mostly empty space. The asteroids within it are typically millions of miles apart from each other, so spread out that a spacecraft can pass through the entire belt without any real risk of colliding with anything, and several have done exactly that without needing to maneuver around obstacles at all. The total mass of everything in the asteroid belt, if you combined every asteroid together, would still be less than the mass of Earth's moon, spread out across a region of space so vast that it makes the asteroids themselves feel almost incidental, scattered specks in an otherwise quiet stretch of the solar system, drifting slowly, each on its own long, lonely orbit around the Sun. If you've ever wondered how astronomers figure out what stars are made of when they're so impossibly far away, the answer comes down to light itself and the way different elements interact with it. When light from a star passes through a prism, or any instrument that splits it into its component colors, it doesn't form a perfectly smooth rainbow. Instead, there are thin, dark lines scattered throughout, places where certain very specific colors are missing. These missing colors correspond to the exact wavelengths of light that different elements absorb. Hydrogen absorbing certain wavelengths, helium others, iron others still, each element leaving its own unique fingerprint in the spectrum of light passing through or around it. By carefully studying these patterns of missing light, astronomers can determine not just what a star is made of, but its temperature, how fast it's moving toward or away from us, and even whether it has planets, by looking for the incredibly subtle rhythmic wobbles those planets cause as they orbit. All of this from light that left its source years, centuries, or millennia ago, carrying within it a kind of chemical signature, a message written not in words but in the specific colors that are missing, decoded patiently, one star at a time. Some of the oldest light we can detect didn't come from stars at all, but from a time before stars existed. For the first few 100,000 years after the Big Bang, the universe was so hot and dense that light couldn't travel freely. It kept bouncing off particles almost immediately after being emitted, the way light might struggle to pass through a thick fog. But as the universe expanded and cooled, it eventually became transparent, almost instantly in cosmic terms, and light was suddenly free to travel in straight lines for the first time. That burst of light, released all at once across the entire universe at that moment, is the cosmic microwave background we mentioned earlier, and it's been traveling, mostly undisturbed ever since, stretching and cooling as the universe expanded around it. When astronomers map this ancient light across the sky, they find it's remarkably uniform, almost exactly the same temperature in every direction, but with extremely tiny variations, fluctuations so small they're measured in millionths of a degree, and these tiny variations are thought to be the seeds from which all of the structure in the universe eventually grew. Galaxies, clusters of galaxies, everything. Tracing back to ripples almost too small to measure, present in the universe's very first light, gravity itself, the force that holds you against the bed right now, that holds the moon in its orbit, and that shapes galaxies across billions of light years, is in some ways the least understood of the basic forces of nature. Einstein described gravity not as a force pulling objects together in the traditional sense, but as a curvature of space and time itself, with massive objects creating dips and curves in this fabric, and other objects simply following the straightest possible path through that curved space. A path that, from our perspective, looks like falling toward the massive object. Imagine a stretched rubber sheet with a heavy ball placed in the middle, creating a dip, and then rolling a smaller ball nearby. It will curve toward the heavy one, not because anything is pulling it directly, but because the surface itself is curved. Earth doesn't pull the moon through empty space in the way a rope might pull a sled. Instead, Earth's mass curves the space around it, and the moon simply follows the natural curve of that space, which happens to be an orbit. It's a strange way to think about something as familiar as gravity, less like a tug, more like a landscape, with everything in the universe rolling gently along the slopes and valleys that mass itself creates. There's a particle called the neutrino that's almost unbelievably common and almost unbelievably difficult to detect. Trillions of neutrinos pass through your body every single second, produced by nuclear reactions in the sun, by distant supernovae, and even by natural radioactivity within the Earth itself. But neutrinos interact with matter so rarely that the vast majority of them pass straight through you, straight through the Earth, straight through nearly everything, without ever touching a single atom along the way. To detect even a handful of them, scientists have built enormous detectors, sometimes filled with thousands of tons of ultra-pure water or other materials, buried deep underground or under ice, waiting patiently for the extraordinarily rare moment when a neutrino actually collides with something and produces a tiny, brief flash of light. In a sense, the sun is sending you a constant, gentle stream of nearly invisible messengers, right now, while you read or listen to this. Messengers that have traveled from the heart of the sun, through millions of miles of space, through the walls of wherever you're lying, through your own body, and onward, into the ground beneath you and out the other side of the planet, almost all of them never even noticing you were there. Quantum mechanics, the branch of physics that describes the behavior of incredibly small things like atoms and particles, includes some ideas that sound less like science and more like riddles. One of the strangest is the idea that, at very small scales, particles don't seem to have definite properties until they're measured or observed in some way. Before that, they exist in a kind of blurred state of possibility, described mathematically as existing in multiple states at once, until something interacts with them and forces a single outcome to become real. This isn't simply a matter of us not knowing the answer ahead of time, the way you might not know the outcome of a coin flip before it lands. It appears to be something deeper, where the outcome genuinely isn't determined until the moment of interaction itself. Particles separated by enormous distances can also become linked in a way that means measuring one instantly affects what you'll find when you measure the other. A connection that doesn't involve anything traveling between them, in the usual sense. A phenomenon so strange that Einstein himself was famously uncomfortable with it. At the smallest scales, the universe doesn't behave the way our everyday experience suggests it should, and the closer physicists look, the stranger and more wonderfully indifferent to common sense it seems to become. Sound, light, gravity, time, all of these things we've talked about exist on scales so enormous or so tiny that they're difficult to really feel in any direct way. But there's something grounding in knowing that the same basic rules apply everywhere, from the smallest particle to the largest galaxy. The same gravity that gently holds you against your mattress tonight is, in a much grander form, holding entire galaxies together. The same light that lets you see the room around you, if there's any light on at all, is made of the same particles that have been traveling across the universe for billions of years. You're not separate from any of this. You're not watching it from outside. You're inside it, made of it, governed by the same quiet, patient rules as everything else. A small, warm part of a much larger, much older system, one that doesn't need you to understand it in order to keep going, but that includes you completely all the same. There's a kind of star called a red dwarf that doesn't get much attention, but it might be one of the most important kinds of stars in the entire universe, simply because there are so many of them. Red dwarfs are smaller, cooler, and dimmer than our Sun, and individually they're not particularly dramatic. No spectacular flares, no dazzling brightness, just a faint, steady red glow. But they make up the vast majority of all stars in the galaxy, far outnumbering stars like our Sun. And because they burn their fuel so slowly, much more slowly than larger, brighter stars, they can last for an extraordinarily long time, potentially trillions of years, far longer than the current age of the universe itself. This means that, in some sense, the universe is still young, at least from the perspective of these stars. Most of them haven't even reached middle age yet, long after our own Sun has swelled into a red giant and faded into a white dwarf, long after many of the brighter, flashier stars in the galaxy have lived their entire lives and died. The vast majority of red dwarfs will still be quietly glowing, dim and patient, barely having begun their incredibly long lives. Some stars don't die quietly at all. When a star much more massive than our Sun reaches the end of its life, it can explode in a supernova so bright that, for a brief period, it can outshine an entire galaxy containing billions of other stars. These explosions are so powerful that they can be seen across enormous distances, and historically, some supernovae in our own galaxy were bright enough to be visible during the daytime, recorded by ancient astronomers who had no idea what they were actually witnessing, only that a new, impossibly bright point of light had suddenly appeared where nothing had been before, sometimes remaining visible for weeks before slowly fading away. These events aren't just dramatic, they're essential, scattering heavy elements out into space, elements that will eventually become part of new stars, new planets, and as we discussed earlier, new living things. Every supernova is, in a strange way, both an ending and the seed of countless beginnings, a single star's death, scattering the raw material for things that won't exist for billions of years afterward. Globular clusters are some of the oldest structures we can observe. Tightly packed spherical collections of hundreds of thousands, sometimes millions, of stars, all gravitationally bound together and orbiting around the outskirts of galaxies. Many of these clusters are nearly as old as the universe itself, containing stars that formed in the very early stages of cosmic history, billions of years before our sun existed. If you could somehow stand on a planet within one of these clusters, assuming such a planet could even form there, the night sky would look completely different from ours, filled with so many bright, close stars that there might be no true darkness at night at all, just a sky glowing softly with the combined light of countless ancient suns, far brighter than any night sky we've ever known, a permanent twilight created not by any single source, but by sheer density, by being surrounded on all sides by stars that have been shining since long before Earth existed. Sometimes, when astronomers look at very distant galaxies, they're essentially looking back in time, seeing those galaxies not as they are now, but as they were when the light left them, sometimes billions of years ago. This means it's possible to look at different parts of the sky and see different chapters of the universe's history simultaneously. Nearby galaxies showing relatively recent history and extremely distant ones showing the universe in its youth, when galaxies were smaller, messier, and still forming. In a sense, looking deep into space is also looking deep into time, and the universe doesn't present itself to us as a single snapshot, but as a layered collection of different eras, all visible at once, depending on how far away, and therefore how far back, you're willing to look. The deepest images ever taken, staring at seemingly empty patches of sky for very long exposures, have revealed thousands of galaxies in regions that appeared completely dark to less sensitive instruments, each one a separate point of light that traveled for billions of years through the vast emptiness between galaxies, just to arrive faintly in a single pixel of a telescope's camera, completing a journey longer than almost anything else you could imagine. Ending here, now, as a tiny part of a picture, even our understanding of what counts as a planet has changed surprisingly recently. For a long time, Pluto was simply considered the 9th planet, without much controversy. But as astronomers began discovering other objects of similar size in the same distant region of the solar system, it became clear that either many of these new objects should also be called planets, or a clearer definition was needed. The eventual decision to define planets more strictly, requiring them to be large enough to have cleared their orbital neighborhood of other debris, meant that Pluto, which shares its region of space with many other icy bodies, no longer fit the new definition, and was reclassified as a dwarf planet instead. This wasn't a judgment about Pluto changing in any way. Pluto itself remained exactly the same icy world it had always been, only our categories, our human systems for organizing and naming things, had shifted. It's a small reminder that even something as seemingly fixed and factual as how many planets are in our solar system depends, at least partly, on the words we choose and the lines we decide to draw, lines that the universe itself never asked for and doesn't particularly care about either way. The night sky has looked different at different points in human history, and it will look different again in the future, even without anything dramatic happening. The stars themselves are all moving, slowly, relative to each other, and over tens of thousands of years, the patterns we call constellations gradually shift and change shape. The Big Dipper that ancient peoples saw thousands of years ago wasn't quite the same shape as the one we see today, and the one our distant descendants will see, tens of thousands of years from now, will have drifted into yet another shape entirely, the stars within it slowly separating or rearranging as each one continues along its own slow path through the galaxy. The constellations feel permanent, feel like fixed landmarks, simply because human history, even all of recorded history, is far too brief a slice of time for these changes to become noticeable. But the night sky has never actually been still. It's simply moving so slowly on such a vast timescale that within any single human lifetime, even within the entire span of human civilization so far, it appears to hold perfectly, comfortingly still. There's a strange irony in the fact that, for most of human history, people had no idea the Earth was just one planet among many, orbiting one star among billions, in one galaxy among trillions, and yet they still managed to track the movements of the sky with remarkable precision. Ancient structures found around the world, built thousands of years ago, were carefully aligned with the rising or setting positions of the sun on specific days, like the solstices, when the sun reaches its highest or lowest point in the sky for the year. Building something so large, so permanent, often using stones weighing many tons just to mark a single moment in the sky's yearly cycle, suggests just how important these patterns were to people, long before anyone had a word for astronomy, long before anyone understood what stars actually were. They watched, they noticed, they built monuments to mark what they saw, and in doing so, left behind a kind of message across time, a record, not of what they knew, but of what they were paying attention to, written in stone, aligned with a sky that, in its broad patterns at least, hasn't changed all that much since. Calendars themselves are, in a sense, an attempt to reconcile different cosmic rhythms that don't quite line up neatly. A day is based on Earth's rotation. A year is based on Earth's orbit around the sun. A month, originally, was based on the moon's cycle around the Earth. But these cycles don't divide evenly into each other. A year isn't an exact whole number of days. It's about 365 and a quarter days, which is why we have leap years, an extra day added every 4 years to keep our calendar roughly aligned with the actual time it takes Earth to orbit the sun. Even leap years aren't quite a perfect fix, which is why there are additional small adjustments made every few centuries. The moon's cycle doesn't divide evenly into a year either, which is part of why months don't line up perfectly with lunar phases anymore in most calendars. In a way, every calendar is a kind of compromise, an attempt to map smooth, continuous cosmic motions onto a tidy grid of numbers, a grid that mostly works well enough for daily life, but never quite perfectly, with the smallest mismatches quietly accumulating, patiently corrected every so often, century after century. Bees can perceive ultraviolet light, a part of the spectrum completely invisible to human eyes, and many flowers have evolved patterns visible only in ultraviolet. Patterns that act almost like landing strips, guiding bees toward the center of the flower where pollen and nectar are located. To us, a flower might look like a single uniform color, but to a bee, the same flower might show a completely different pattern, with markings and contrasts that simply aren't there as far as our eyes are concerned. It's a quiet reminder that the world doesn't look the same to everything that lives in it, that there are entire visual languages happening all around us, in gardens, in fields, written in light we can't see, conversations between flowers and insects that have been going on for longer than there have been eyes to read them in the way they were intended, a private correspondence happening in plain sight, all day, every day, completely outside of human perception. Birds that migrate long distances sometimes do so at altitudes and over distances that are hard to comprehend. Certain birds fly non-stop for days at a time, crossing entire oceans without ever landing, sleeping in short bursts while still in flight. sometimes letting one half of their brain rest while the other half continues to manage flight, similar to the way some marine mammals sleep that we mentioned earlier. Some birds fly at altitudes high enough that the air is thin and cold enough to be dangerous for humans without special equipment, navigating using a combination of the sun's position, the stars, Earth's magnetic field, and even, in some cases, their sense of smell, layering multiple senses together into a kind of internal map that's been refined over countless generations. A small bird weighing only a few ounces might, over the course of its life, fly a distance equivalent to traveling to the moon and partway back, all of it powered by nothing but the energy stored in tiny amounts of fat, built up before each journey, a fuel tank smaller than a coin, somehow sufficient for thousands of miles. Honey, unlike almost any other food, can last for an extraordinarily long time without spoiling, sometimes for years, even centuries, under the right conditions. Archaeologists have found pots of honey in ancient tombs that, despite being thousands of years old, were reportedly still edible, the honey having simply crystallized over time rather than spoiling in the way most foods would. This is partly due to honey's low moisture content and natural acidity, which make it an extremely difficult environment for bacteria to survive in. In a way, a jar of honey sealed away thousands of years ago untouched would have remained essentially unchanged, sitting quietly in the dark for all that time, a small pocket of something edible, preserved by nothing more than its own basic chemistry, patiently waiting, long after everyone who made it had been gone for longer than most civilizations have existed. Mountains are, geologically speaking, still very much alive, in the sense that they're constantly changing, just on timescales far too slow for us to notice directly. The same forces that push mountains upward, the slow collision of tectonic plates, are matched by forces that wear them down: wind, rain, ice and gravity, slowly eroding rock, grain by grain, over millions of years. Some of the oldest mountain ranges on Earth were once far taller than they are today, worn down over hundreds of millions of years into the smoother, more rounded shapes we see now, while younger mountain ranges, still actively being pushed upward, remain jagged and sharp, not yet worn down by time. A mountain range you might look at and think of as permanent, as something that has simply always been there, is actually somewhere in the middle of an extremely slow story, being built up and worn down at the same time, the balance between those two processes determining whether it grows taller, shrinks shorter, or holds, for a little while, somewhere in between. Rivers, too, are constantly reshaping the land around them, even rivers that look calm and unchanging from year to year. Over time, a river will naturally meander, curving back and forth across a floodplain, eroding the outer edges of its bends while depositing sediment on the inner edges, slowly shifting its own course across the landscape. Sometimes a river's curve becomes so pronounced that it loops almost all the way back on itself, and during a flood, the river might cut straight across the narrow neck of land separating the two ends of the loop, suddenly taking a shorter, more direct path and abandoning the old curve entirely. That abandoned curve, cut off from the main flow, can become a quiet, crescent-shaped lake, sitting beside the river that used to pass through it, a kind of geological scar, or perhaps more gently, a memory, marking where the river used to be before it decided, all at once, during a single flood, to go somewhere else instead. The color of the sky itself is the result of a kind of accident involving the size of molecules in our atmosphere and the wavelengths of sunlight. Sunlight contains all colors mixed together, appearing white or pale yellow to our eyes. But as that light passes through the atmosphere, it collides with tiny molecules of gas, mostly nitrogen and oxygen, and shorter wavelengths of light, the blues and violets, get scattered in all directions, far more than longer wavelengths like red and orange. This scattered blue light reaches our eyes from all directions across the sky, which is why the sky appears blue rather than the white or yellow color of the sun itself. At sunset, when sunlight has to pass through a much thicker slice of atmosphere to reach your eyes, even more of the blue light gets scattered away before it arrives, leaving mostly the longer wavelengths, the reds, oranges, and pinks, which is why sunsets often glow in warm colors that the sky doesn't show during the middle of the day. The same sunlight, taking a longer path, arriving looking like a completely different color by the time it gets to you. Mirages, those shimmering illusions of water on a hot road, or distant objects that appear to float above the horizon, are caused by light bending as it passes through air of different temperatures. Hot air near the ground is less dense than the cooler air above it, and light, traveling through these different layers of air, bends slightly, in a way that can create an image that looks like a reflection, even though there's no actual water there at all. What you're seeing in a hot road mirage is often a distorted reflection of the sky itself, bent by the layers of hot air just above the road's surface, creating something that looks remarkably like a puddle from a distance, but that disappears entirely as you get closer, because the angle at which the bent light reaches your eyes changes as you move, the illusion existing only from certain positions, for certain people, at certain moments, a trick of light that has no fixed location at all, only a fixed relationship between you, the air, and the sky. Echoes happen because sound, like light, takes time to travel and can bounce off surfaces. If you shout toward a distant cliff or large wall, the sound waves travel outward, reflect off that surface, and travel back to your ears, arriving slightly later than the original sound you made. If the distance is great enough, this delay becomes noticeable as a distinct echo, a repetition of the sound after a brief pause. In certain large, empty spaces like big caves or canyons, sound can bounce off multiple surfaces, arriving back at slightly different times from slightly different directions, creating echoes that themselves echo, fading gradually rather than stopping abruptly, the original sound slowly dissolving into the space around it, scattered and softened, taking longer to fade than it took to make in the first place, the space itself seeming to hold onto the sound for just a little while after you've stopped making it. Deserts, often imagined as endless flat expanses of sand, are actually some of the most varied landscapes on Earth, and many deserts aren't sandy at all, but rocky, or covered in low scrub vegetation, adapted to survive on very little water. What defines a desert isn't heat, but dryness. Some of the coldest places on Earth, including parts of Antarctica, technically qualify as deserts because so little precipitation falls there. In hot deserts, the temperature can swing dramatically between day and night because dry air and a lack of cloud cover mean that heat absorbed during the day radiates away quickly once the sun sets, with nothing to trap it close to the ground. A desert that feels unbearably hot during the afternoon can become surprisingly cold once night falls. The same patch of ground experiencing two completely different climates within a single day, simply because there's so little moisture in the air to even things out, to hold on to the day's warmth and release it slowly through the night, the way more humid places do. Even something as ordinary as a puddle reflects an enormous amount of what's happening above it, in a literal sense. When you look down at still water, You're seeing a near-perfect mirror image of the sky, the clouds, anything overhead, flipped and reversed, a small patch of ground temporarily containing an entire upside-down sky within it. The smallest disturbance, a single raindrop, a breath of wind, a passing insect, ripples that reflection outward, breaking the mirror into moving fragments before it settles again, smooth and still, holding the sky once more, at least until the next small disturbance arrives. There's something quietly poetic about it, the idea that even the smallest, most overlooked bits of water lying around after a rainstorm are, in their own way, briefly holding onto a piece of the sky, reflecting it back, faithfully, for as long as the surface remains calm enough to do so. Far above the clouds, far above where airplanes fly, there's a layer of the atmosphere where temperatures can drop low enough for very thin, very high clouds made of ice crystals to form, sometimes visible only at twilight. Glowing faintly after the sun has already set below the horizon for everyone on the ground. These are called noctilucent clouds, meaning night shining, and they're among the highest clouds in Earth's atmosphere, so high that they're lit by sunlight even when the sun itself has already disappeared from view for an observer on the ground, sunlight grazing the upper atmosphere at an angle, illuminating these delicate, wispy clouds from below while the rest of the sky has already gone dark. They're rare and beautiful, and a little bit eerie, a faint silvery blue glow appearing in part of the sky long after sunset, as if a small piece of daytime had been left behind, lingering quietly far overhead, visible for just a little while before it, too, fades into the ordinary dark of night. The very air you're breathing right now has a history that stretches back much further than you might expect. The oxygen in Earth's atmosphere wasn't always there in the amounts we have today. For a very long time, early in Earth's history, the atmosphere contained very little oxygen at all. It was tiny organisms, ancestors of what we now call cyanobacteria, that began producing oxygen as a byproduct of an early form of photosynthesis, slowly, over an enormous span of time, changing the composition of the entire atmosphere. This shift, sometimes called the Great Oxidation Event, took place over hundreds of millions of years, and it fundamentally changed what kinds of life could exist on Earth, eventually allowing for the kinds of complex oxygen-breathing organisms that would come much, much later, including, eventually, us. Every breath you take tonight is, in a sense, part of a process that tiny organisms started billions of years ago, and that has never really stopped since, a slow exhale from the deep past, still going, still filling your lungs, one breath at a time. Fossils themselves are far rarer than people sometimes assume, not because so few things died, but because the specific conditions needed for something to become a fossil are quite particular. Most living things, when they die, simply decompose completely, leaving nothing behind. For something to fossilize, it usually needs to be buried relatively quickly, in conditions that slow down decomposition, often in fine sediment near water, where minerals can gradually replace the original organic material over a very long time, slowly turning bone or shell, or even, in rare cases, soft tissue, into stone, while preserving the original shape in remarkable detail. This means that the fossil record, the snapshot of ancient life that we have access to, is really only a tiny, biased sample weighted toward creatures that happened to die in just the right places under just the right conditions to be preserved for millions of years afterward. Countless other forms of life almost certainly existed and left no trace at all. Their entire existence, every individual that ever lived, leaving behind nothing we'll ever be able to find. simply because the right grain of mud wasn't there at the right moment, in the right place, at the time they happened to die. Amber, the fossilized resin of ancient trees, occasionally preserves something even rarer than bones, tiny insects, sometimes even small amounts of soft tissue, trapped the moment they became stuck in sticky tree sap millions of years ago, before that sap slowly hardened and fossilized around them. Inside some pieces of amber, scientists have found insects so well preserved that individual hairs, wing veins, even tiny details of their eyes are still visible, an organism that lived and died in a single brief moment, millions of years ago, captured mid-motion, sometimes even caught in the act of doing something, walking, flying, interacting with another insect, frozen there ever since, a tiny scene from an incredibly distant past, preserved with a level of detail that for almost anything else from that long ago simply doesn't exist. There are lakes on Earth that don't freeze even in extremely cold conditions, and lakes that exist beneath thick layers of ice, completely sealed off from the surface for what might be millions of years. In parts of Antarctica, deep beneath the ice sheet, there are lakes of liquid water, kept liquid not by warmth from above, which doesn't exist there, but by heat rising from the earth below, combined with the immense pressure of the ice on top, which lowers the freezing point of water. These subglacial lakes have been isolated from the rest of the world for an enormous amount of time, and when scientists have managed to drill down and sample them carefully to avoid contaminating these ancient, sealed environments, they've sometimes found microbial life, organisms that have been living in complete darkness, in extreme cold, cut off from sunlight and from the surface world for far longer than human history has existed, a hidden world existing this entire time, completely sealed away, just beneath one of the most familiar, most photographed landscapes on the planet. If you've ever skipped a stone across water, you've used a principle that, on a much larger and more dramatic scale, also explains how spacecraft sometimes use a technique called a gravity assist, or slingshot maneuver, to gain speed without using any fuel at all. By carefully aiming a spacecraft to pass close by a planet, the spacecraft can essentially borrow a tiny bit of the planet's orbital momentum, gaining speed relative to the Sun, while the planet itself, being so much more massive, loses an amount of speed so small it's completely immeasurable. Some spacecraft have used multiple gravity assists from different planets, one after another, bouncing gently from planet to planet, each encounter adjusting their speed and direction slightly, like a carefully choreographed sequence of skips across an enormous cosmic pond, eventually reaching speeds and destinations that would have been impossible to achieve with the fuel they were able to carry alone, the gravity of entire planets doing quiet, patient work that no engine on board could manage by itself. There's something quietly humbling about realizing that almost everything in the universe exists on a timescale that makes a single human life seem impossibly brief, and yet, at the same time, your life is happening at the exact moment, in the exact place, where all of that history has led. The carbon in your body took billions of years to be created inside stars and scattered across space. The water that makes up most of your weight has likely existed, in one form or another, cycling through oceans, clouds, rivers, and living things, for longer than there have been humans to drink it. The ground beneath wherever you're lying has been shaped by processes, mountains rising and eroding, continents drifting, that have been going on since long before anything resembling a bed, or a room, or a person existed at all. And yet here you are, right now, at the end of all of that, not separate from it, not just observing it from the outside, but made of it, shaped by it, the temporary, living result of an almost unimaginably long and patient chain of events, simply lying there, breathing, about to fall asleep. Sleep itself connects you to that long chain in a way too. Every night, your body undertakes a kind of quiet maintenance, repairing tissues, consolidating memories, clearing away certain waste products that build up in the brain during waking hours. Some research suggests that during deep sleep, the spaces between brain cells actually widen slightly, allowing fluid to flow through more easily and flush out some of these byproducts, almost like a nightly cleaning cycle that can only really happen properly while you're unconscious, while your brain isn't busy directing your attention outward toward the world. In a sense, falling asleep isn't just stopping, it's switching into a different kind of activity, one that's just as essential as anything you do while awake, just quieter, slower, and almost entirely hidden from your own awareness. Happening in the dark, behind the scenes, every single night, whether you think about it or not. Dreams themselves remain one of the more mysterious aspects of sleep, something almost everyone experiences, and yet something science still doesn't fully explain. During certain stages of sleep, particularly the stage associated with rapid eye movement, brain activity can actually resemble, in some ways, the activity seen during wakefulness. Even though the body remains mostly still, in a kind of temporary paralysis that prevents you from acting out whatever's happening in the dream. Some researchers think dreams might play a role in processing emotions or in consolidating memories, weaving new experiences together with old ones in ways that might help with learning. Though there's still a lot we don't fully understand. What we do know is that every night, in nearly everyone, the brain generates entire experiences, vivid sometimes, strange sometimes, often forgotten within minutes of waking, a kind of private, internal world that gets created and then mostly dissolved, over and over, every single night, for as long as a person lives. Almost none of it ever shared, almost all of it forgotten. Vanishing quietly each morning like mist. There's a particular kind of quiet that settles over a place late at night, different from the quiet of an empty room during the day. Part of it is simply that there's less activity, fewer cars, fewer voices, fewer of the small background sounds that fill a typical day without us even noticing them until they're gone. But part of it might also be something gentler, a kind of collective stillness, the sense that across a city, across a neighborhood, in countless rooms not too different from yours, other people are also lying down, also closing their eyes, also letting go of the day, all at roughly the same time, each of them in their own small private world, and yet all of them doing, in a way, the same thing, together, without ever needing to say so. Night doesn't really separate people the way it might seem to. In a strange way, it's one of the most universal experiences there is, something nearly everyone does, every single day, the world quietly synchronizing itself into rest, region by region, as the sun moves on to somewhere else. If you think about it, the boundary between day and night isn't a hard line at all. It's a gradual, moving gradient, sweeping continuously around the planet as Earth rotates. At this very moment, somewhere on Earth, the sun is rising. Somewhere else, it's setting. Somewhere it's the middle of the afternoon, and somewhere else, the deepest part of the night. None of these moments are more real or more correct than any other. They're all simply happening, at the same time, in different places, each one valid from where it's experienced. The day you had today is already over in some places and hasn't even started yet in others. There's no single official version of right now, just countless overlapping versions of it, each one true for someone, somewhere, all of them existing simultaneously. All of them part of the same single, continuously turning planet. And so, as the night continues here, wherever here happens to be for you, somewhere else the morning is just beginning. Somewhere, the first light is touching rooftops. Somewhere else, people are waking up, starting their day, completely unaware of the quiet you're sitting in right now, just as you, most of the time, are unaware of theirs. It's a strange, gentle kind of connection, knowing that the planet you're on is always, at every moment, holding every part of the day at once, sunrise and sunset and midnight and noon, all happening together, all the time, everywhere, a planet that never fully sleeps, even while large parts of it, including very soon you, settle quietly into rest. Far out in the solar system, beyond even Neptune, there's a small world called Sedna that takes about 11,000 years to complete a single orbit around the Sun. Its path is so elongated that, at its closest approach, it's still much farther from the Sun than Pluto, and at its farthest, it travels out into a region so distant and so cold that almost no sunlight reaches it at all, just a faint point of light, barely brighter than the other stars, marking where our Sun is from that incredible distance. Whatever the conditions are like out there, at the far end of Sedna's orbit, they've barely changed in thousands of years, and won't change much for thousands more. A tiny world tracing an enormous, lonely ellipse through the dark, taking longer to complete a single loop than human civilization has existed, moving so slowly, relative to its vast path, that from our perspective it might as well be standing still, drifting through the outer dark on a schedule that dwarfs anything we usually think of as long. Even something as simple as walking involves a kind of controlled falling that most people never think about. With each step, your body tips slightly forward, off balance, and your leg swings forward to catch you, turning what would otherwise be a fall into a smooth, repeating motion. In a sense, walking is just a series of small, carefully timed falls, one after another, each one caught just in time by the next step, your body using gravity itself as part of the mechanism that moves you forward. It's such a basic, automatic motion that almost nobody thinks about it this way. And yet it's a small, everyday example of the same force that holds the moon in orbit and shapes the paths of galaxies, working quietly, at a much smaller scale, every time you cross a room, gently pulling you forward, step after step, the same patient force at every scale, from the smallest stride to the largest spiral of stars. The color of a flame can tell you something about how hot it is, and in a way, this connects back to the same idea we mentioned earlier about starlight. A candle flame is mostly orange and yellow near its base, where it's cooler, and can appear blue near the very hottest part, close to where the fuel is burning most efficiently. Hotter things tend to glow with shorter wavelengths of light, bluer light, while cooler things glow with longer wavelengths, redder light, the same basic principle that helps astronomers estimate the temperatures of distant stars just by looking at their color. A red star is, relatively speaking, cooler than a yellow star like our Sun, which in turn is cooler than a blue star, some of which can be many times hotter than the Sun, burning through their fuel so quickly that, on a cosmic timescale, they live remarkably short lives, bright and blue and brief, compared to the slow red dwarfs that can glow gently for trillions of years, the color of a flame and the color of a star. In the end, telling a similar quiet story about heat and time and how long something is likely to last, there's a kind of stillness that exists at the very top of certain mountains, above where most weather happens, in a thin, cold layer of air, where the sky often appears a deeper, darker blue than it does at lower altitudes, sometimes shading almost toward violet near the edges of vision. With less atmosphere above to scatter light, the sky loses some of its usual brightness, and on very clear days, from high enough up, it's sometimes possible to see stars even while the sun is still above the horizon. Something that's essentially impossible from sea level, where the brighter, thicker atmosphere washes out all but the very brightest objects in the sky. Climbers who've reached extreme altitudes have sometimes described this, a sky that looks almost like night despite the sun still being visible, a strange overlap of day and night occurring in the same view, simply because there's so little air left between them and space to blur the difference. And so, the universe really does seem to repeat its patterns at every scale. Gravity in a footstep and gravity in a galaxy, light in a candle flame and light from a star, falling drops of water shaping stone over centuries, and falling photons shaping our understanding of the cosmos over billions of years. Nothing about tonight, this room, this bed, this breath, is separate from any of that. It's all the same universe, doing the same kinds of things, just at different sizes, different speeds, different distances. Wherever you are right now is simply one more place where all of that is quietly, continuously happening, the way it always has, the way it always will, with or without anyone noticing. Though tonight, for a little while, you did. We've drifted through a lot tonight. From the 8 minutes it takes sunlight to reach your skin, to the trillions of neutrinos passing harmlessly through your body every second. From black holes that stretch anything that falls toward them, to honey that can outlast civilizations. From the slow drift of the moon, inch by inch, year by year, to the fast spin of Jupiter, completing a day in less time than it takes you to sleep through the night. From oceans hidden under ice on faraway moons, to oceans of liquid metal turning slowly beneath your own feet, generating the very field that paints the sky green and purple near the poles. None of these facts need to be remembered. None of them are a test. They're just small windows, little glimpses into how strange, how layered, how quietly astonishing the ordinary universe actually is. Once you start looking closely enough, what's strange is that almost none of this changes anything about your day tomorrow. The sun will still rise the same way it always has. The kettle will still take the same amount of time to boil. None of these facts make the world more complicated to live in. If anything, they might make it feel a little softer, a little more spacious, a reminder that everything you know, every room you've ever been in, every person you've ever met, every ordinary Tuesday, has been happening this entire time inside something vastly larger, older, and stranger than any of us usually stop to think about, and yet none of it has ever needed our attention in order to keep going. The universe was doing all of this, the starlight, the gravity, the slow drifting of moons and the slow churning of molten metal, long before you were born, and it'll keep doing it. Quietly in the background, long after, not because it has anywhere to be, but simply because that's what it does. There's a comfort in that, if you let there be. You don't have to hold any of this up. You don't have to keep the stars burning, or the earth spinning, or the tides moving, or your own heart beating, not consciously, not through any effort of will. All of that is simply happening, has been happening, will keep happening, with or without your attention, tonight and every night. Your only job, if you want to call it that, is to let go, to stop holding on to the day that's ending, and let yourself become, for a little while, just another quiet, breathing part of all this motion drifting along with everything else, the way a leaf might drift on a slow river, not steering, not working, just being carried gently along by something far bigger than itself, something that's been moving long before the leaf arrived and will keep moving long after. If your mind is still busy, still turning over thoughts from today, that's all right too. You don't have to push them away. You can simply let them be there, quietly, in the background, the way the stars are quietly there in the daytime sky, even though you can't see them. They don't disappear just because your attention moves elsewhere. They're still there, waiting, patient, the way they always are, and they'll still be there tomorrow if you need them. For now, there's nothing that needs solving, nothing that needs deciding. Just this moment, this breath, this soft weight of the blanket, this quiet, dark room, somewhere on a planet that is, right now, as it always is, half in daylight and half in night, turning slowly, the way it has for billions of years, the way it will for billions more. Think, if you'd like, of all that starlight, still traveling, right now, through the dark, on its way to somewhere. Some of it is heading toward Earth, due to arrive in 100 years, or 1,000, or 1,000,000. Light that's already left its star, already begun its long journey, with nothing left to do now but travel, slowly, steadily, through the emptiness, toward a destination it'll reach long after the star that made it has changed, or faded, or gone. There's something gentle about that image. Light that's already on its way, already decided, already moving, with nothing more required of it than to simply continue. The way your own breathing continues, in and out, without you needing to think about it, each breath simply following the one before, on its way towards sleep, and somewhere, very far from here, in the cold and the dark, between galaxies, past the edge of everything we can see, space is quietly stretching, slowly, gently, the way it has for billions of years, making more room, more distance, more dark, more quiet. You don't have to picture all of it. You don't have to hold the whole universe in your mind at once. Nobody could. Just let your thoughts settle on whatever small piece of it feels calming. A single star, a single drop of water, a single quiet lake hidden under ice somewhere far away. Anything small enough to hold gently, anything that helps your mind slow down, the way the body slows down, breath by breath, heartbeat by heartbeat, toward rest. The night will go on without you needing to watch it. The stars will keep their positions, more or less, for tonight at least, drifting only by amounts too small to notice. The tide will keep its rhythm, the moon its slow retreat in, the magnetic field its quiet hum beneath the ground. None of it is waiting for you to fall asleep, and none of it needs you to stay awake either. It will simply continue the way it always has, the way it always will, patient and steady and completely unconcerned with the time. So if you're ready, you can let go now. Let your thoughts soften. Let your breathing slow. Let the weight of the day finally settle down into the mattress beneath you. The same gravity that holds galaxies together gently holding you in place too. Nothing dramatic, nothing complicated. Just a soft, steady pull, keeping you right where you are, safe, still, and quiet. If you're still listening, thank you for spending this time here, drifting through all these small, strange facts about the universe with me. If this helped you relax even a little, you're welcome to come back another night whenever you need it. There's no rush, no pressure, nothing left to do now. Just rest. Let the room go quiet. Let your eyes stay closed. Let the night carry on, the way it always does, the way it always will, long after this voice has gone quiet too. Good night, and sleep well.